Hello everyone, my name is Bai. This is our presentation for CS 536 final project, building an GPT app. We call it ChatGPT. My other two teammates are Gilbert and Ziyang. Let's first give a glance of the overview of our project. Our objective of the project is developing an app that can use ChatGPT on mobile and enable speech-to-text and text-to-speech technologies. We choose to use Swift UI as our front end while enabling speech-to-text and text-to-speech. Since we want to create a cross-platform app, we choose Python as our backend language, and we use a library named Flask as the messenger to communicate with the client. The OpenAI API we chose is GPT 3.5, but it also supports GPT-4. Let's first watch a short demo of our app.
How are you today?
I'm good, thanks. How about you?
I'm good. Can you introduce yourself?
Sure, I'm an AI language model designed to assist with various tasks, including answering questions and providing information. Is there anything specific you'd like to know?
Can you briefly explain congestion control and flow control?
Conjunction control refers to the use of conjunctions, such as and, or, but, to connect words,
As you can
phrases,
see,
or clauses in a
this
sentence. It
demo
helps to
demonstrates
enhance
that we
relationships
enable
between different elements
speech-to-text
in a
and
sentence. Flow
text-to-speech
control, on the
technology
other hand,
and the
refers to the
fluent
management and
communication with
execution of
GPT
order statements or
3.5.
instructions in a program. It allows for
Let's take a
conditional
closer
conditioning,
look
looping,
at the
and
backend's
decision-making within a program to
message
control the
process
flow of
flow.
execution.
This detailed view correlates directly with our server code, showing exactly how we handle communication in real time. The first step is receive user message. Our journey begins when a user sends a message. The Flask server is configured to listen for incoming post requests at the receiver message route. As soon as the message hits its endpoint, we grab the content from the JSON payload using message equal to data get message. And the second step is pre-process the message. The backend server pre-processes the message and convert it to a JSON file. And the third step, the backend sends the message to the GPT API. The preprocessed user message then passed to our chatbot generate response function. The function works along with the OpenAI integration module to send the message to GPT API. And the fourth step, we receive an API response. Our OpenAI integration module does the work off screen, communicate with the GPT model and waiting for the generate response. Once received, it is handled back to the Flex server, and we record the corresponding latency for future research. And the fifth step is post-processing the response. In the generated response method in chatbot.py, any necessary post-processing will occur. This involves additional cleaning or formatting. The focus is to keep the response swift and accurate. The final step is send the response back to the user. The Flask server packet the bot's response along with a timestamp and the response time in milliseconds. This is not only delivers the answer, but also provide a valuable metric. Through this flow, we maintain a log of conversation, which is crucial for any learning and improvement. Each interaction is a blend of Flask web capability and the GPT API's powerful language model. This ends the introduction of the backend, and now Zian will talk about the front end.
Now let me introduce the front end, the client and the mobile app. Starting with the UI design. Our UI design is inspired by ChatGPT mobile app developed by OpenAI, specifically modeled after the design demonstrated in the full course Swift UI chat app tutorial by Jason Dubon on YouTube. After launching the app, users can see a pretty clean interface similar to other messaging apps. At the bottom of the screen, there is a text box with a blue button on the right of it. Since our project focuses on voice interactions, we disable the message sending functionality through the text box. The blue button is the record button. It is a gateway to our speech-to-text transcription feature. When activated, it seamlessly converts spoken words into text, thanks to the integrated speech-to-text engine. We'll talk about it more later. As the user concludes their spoken input and presses the stop button, their message is visually encapsulated in a message bubble on the right side of the screen. Simultaneously, this input is dispatched to our backend server. Here, it's processed and relayed to GPT, which then crafts a response message. This response is promptly displayed in the left column, ensuring a conversational flow. For users wishing to clear the historical messages, there is a clear button placed on the upper right corner to delete historical interactions. Moving on to the voice chat implementation for converting human speech to text and vice versa. The foundation of our speech-to-text feature is the class named Speech Recognizer, implemented by following the guidelines and examples from Apple's iOS app development tutorials. This class enables real-time transcription of spoken words. It is initiated when a user taps the record button, activating the system's audio engine to begin transcribing spoken words into text. For text-to-speech component, we leverage the built-in iOS class AV Speech Synthesizer. Since it is pretty straightforward to use and is well documented in the Apple developer documentation. This integration allows for a seamless conversion of text responses into audible speech. Once we receive a response from the server, it is transformed into an object known as utterance. This utterance is then passed to the synthesizer, which articulates the message audibly, providing users with an interactive conversational experience. When the user's spoken words are transcribed into text by our system, the next step is to prepare this data for transmission to our server. We achieve this by encapsulating the transcribed text into a JSON format, a standard protocol for data exchange. To transmit this data, our application employs a built-in function called URL request. We utilize this function to create a post request, where the HTTP body is set to contain the user's message in JSON format. This setup enables us to efficiently and reliably send the user's input to our server. Upon receiving the response from the server, which is also delivered in JSON format, our app performs two key actions. First, it extracts the response message from the JSON payload, and second, it calculates the round-trip time for this entire process. It is important to note that the round-trip time calculation here only accounts for the network duration and does not include the time taken by communicating with GPT to generate the response. This distinction is crucial for accurately measuring the efficiency and speed of our network communications, separate from the processing time of the GPT model. To evaluate our app's performance, we set up a testing environment that reflects a variety of real-world scenarios. Our server, hosted on Oracle Cloud Platform, operates from a data center in Phoenix, Arizona. The app was built and installed on an iPhone 15 Pro running the latest iOS version 17.1.2. There's also a key step in our training setup, which was to disable the option that uses cellular data to optimize Wi-Fi performance. Our tests were conducted in several environments to assess consistency and reliability. The first one is the home environment where a Wi-Fi network is available. Here, we found the round-trip time to be the most consistent across all our tests. This indicates a stable performance in a typical home setting. Next is outdoor Purdue campus. In this setting, characterized by the availability of 5G networks, we observed low latency, demonstrating the app's effectiveness in outdoor high-speed network environments. However, while using 5G inside the Lawson building, we noted higher latency compared to outdoor settings. More significantly, when moving underground, the RTT increased dramatically, sometimes even triggering timeout errors in our client application. The last one is using 4G network. Our tests with 4G networks showed relatively stable performance both outside and inside the Lawson building, including underground areas. However, we did encounter instances of significant latency spikes. Now it raises a question: how can we improve that? To tell you more about it, here's Gilbert.
To improve the performance under different network conditions, we implement an additional feature, the congestion avoidance. This is implemented in our mobile app. The algorithm is intuitive, way to send the message when network condition is good. If there is no congestion, we send the message immediately as usual. When the congestion is detected, the algorithm will wait for a short period and detect the congestion again. In the next detection, if the congestion is not detected, we will send a message. However, if congestion is still present upon reevaluation, we will transmit the message in next cycle regardless. This ensures that the waiting time does not exceed the actual latency caused by the congestion. To demonstrate the effectiveness of our congestion avoidance, let's consider a hypothetical scenario. When congestion is present, the latency for sending and receiving message is, for example, 0.3 seconds. And without congestion, this latency drops to 0.1 seconds. By using our congestion avoidance, if congestion is detected and then clears before the second detection, the total latency is only 0.2 seconds. We can see a reduction of 0.1 seconds compared to immediate transmission during congestion. To test the performance of the algorithm, we have designed an experiment. We update a large game on Steam to consume the bandwidth in LAN while using our ChatGPT in order to simulate the network congestion. We ask same question to the ChatGPT 15 times with and without congestion avoidance. Let's look at the chart on the right side. The first column is the RTT of the message without congestion avoidance. Obviously, the time with congestion is around 1000 milliseconds, and the time without congestion is around 200 milliseconds. The second column is the RTT of the message with congestion avoidance. There is a DLYD column that denotes whether there's congestion. The row RTT means the pure RTT for message sending and receiving. But remember that when congestion is detected, we'll wait for 0.1 second. Therefore, the adjusted RTT is a sum of the row RTT and the 0.1 second. From the data we collected, we can see that the average RTT of the message with congestion avoidance almost cut into half. We also perform hypothesis testing to see if the difference is significant. The p-value is 0.046, which is less than 0.05. We can conclude that the difference is significant. Our method really reduced the network latency based on our statistical analysis. However, when we conduct the experiment, we didn't feel that much difference. We believe that this is because the ChatGPT server contributes the most portion of the time we wait for a response. A reduction in networking time does not make us feel very different. So this can still be our next step, improve network performance for our project. That's all for our presentation. Thank you for listening.